In this video, we are going to look at light as a wave, and we are going to show that if we take Maxwell's equations, the set of all of our electric and magnetic field equations, together in an empty space environment, that is with no charges or currents, that we actually find that the electric and magnetic fields propagate like a wave. So we begin just by reviewing Maxwell's equations. This is the set of all of the equations that we've looked at throughout the semester for the electric and magnetic fields. To begin with, we have Gauss's law here, which tells us about the electric field due to charges inside of some bounded Gaussian surface. We also have Gauss's law for magnetic fields, which simply says that there are no magnetic sources. So here we have electric sources, sources of electric field, electric charges. Here we say, oh, there are no sources, point sources for magnetic fields. Our magnetic fields always come from moving electric charge as per the Maxwell Ampere equation. Okay, so this is Gauss's law for the electric fields and magnetic fields. We also have Faraday's law, which tells us about the induced electric field due to a changing magnetic flux. So the integral around some closed surface of the electric field looks like the derivative of the magnetic flux with respect to time. And we rewrite the magnetic flux explicitly as an integral of the magnetic field dotted with the area vector. Finally, we have the Maxwell Ampere law, where we have the standard integral of B dot dl equals mu naught I enclosed. So this gives us the magnetic field due to currents of charge. Plus, we have this extra term here, which is the kind of dual to this term, right? So this term tells us that changing magnetic flux creates electric fields. And this term here tells us that changing electric flux gives us magnetic fields. So when we're looking at the source-free magnetic Maxwell's equations, well, we're going to set Q and I to 0. So the first two equations are both equal to 0. And then the next two equations, we have our integral here. We left out the I enclosed because we said I is 0. And so we have an integral around some closed loop. This is dl. We're integrating around some closed loop is equal to the change in magnetic flux through that loop. And we have the integral of the magnetic field around some closed loop equal to the change in the electric flux through that loop. Before we move on, I just want to quickly note the similarities and differences between these equations. So it looks like we have an integral of E dot dA equal to 0. And then down here, it looks like we want to take a time derivative of that same integral and set it equal to the magnetic field, this integral of the magnetic field. Now, really, these are two different integrals because of this little loop symbol here. So this loop means closed surface. So what this integral is saying is that if I take some closed surface, so something like a soccer ball, right? Like a sphere, where we have the surface of that sphere, and we know it's closed because if I start at the center of the soccer ball, I have to go through, so I'll put like a little box there. I had to go through the surface in order to get out of the sphere, right? So the sphere is a closed surface, and the integral of the electric field around that closed surface is always 0 if we do not have any sources. However, for these two equations, for Faraday's law and the Maxwell Ampere law, we are not talking about a closed surface. We are talking about a kind of open surface. So what we're doing is this integral of B dot dl, this is around a closed loop. So I have some length, and that length is closed. So for example, I could make a square box. and I could integrate the magnetic field around that square box. And the E dot dA, this flux, is the flux through that surface. Now this is an open surface because I can get from one side of it to the other without going through the surface. I just kind of walk around the surface. So the integral of E dot dA, the electric flux through an open surface, does not have to be zero. And the same thing is true for this Gauss's law for magnetic fields and our Faraday's law. We're going to take an open surface, and so just because this integral is zero does not mean that this integral is zero. To begin to derive electromagnetic waves from Maxwell's equations, let's think about empty space in which we have an electric field here and some magnetic field, where we will just generically think of some magnetic field in the region for the moment of B. So in this region there is some magnetic field, and that magnetic field may be changing over time. In fact, we really want it to be changing over time because we're going to want to take a derivative of it over time. Okay, so here we have an electric field along the x-axis. I have drawn two different electric field strengths here along the x-axis. And what we want to do is we want to integrate around some closed path the electric field. Now we're going to choose our closed path very cleverly to make the math as easy as possible. So what we're going to do is we're going to create a closed path that simply follows the x-axis, then follows the z-axis. So we have our x-axis to the right, our z-axis up, and our positive y-axis is into the board. This creates a right-handed coordinate system such that x cross y equals z. So our loop is just going to be a square that follows either the electric field lines or is perpendicular to the electric field lines. So this loop here is our dl. So using this, we can write the integral of E dot dl is simply equal to, we're going to do this kind of piecewise. So we're going to do this bottom section, then this section, then the top, and then the bottom, right? And all we're going to do is take our electric field and we're going to dot it with that individual length element, right? So what we're going to do here, our electric field is clearly just in the z direction. So it's just E1 z hat. And our electric field number 2 is clearly also just in the z direction. So we'll write it as E2 z hat. So let's begin our integral by looking at this right section here. Well, we have some little dl, so let's give some dimensions to our box. Let's say that it has a height of h and a width of delta x. So my dl, my integral of E dot dl for number 1, well, my electric field is constant along this line. So this is just E1 z hat dotted with h z hat. My electric field, sorry, this should be E2. My electric field strength is E2. It is, the electric field is moving in the z hat direction. I am dotting it with the distance h, which also points, because my little red arrow points up in the z hat direction. And I've been able to remove the integral because the electric field is constant through this. So the integral of E dot dl is really just E times length, the electric field along this little section multiplied or dotted with the length here. So I've been able to eliminate my integral. Okay, so that's number 1. If I call this section on the top here number 2, well, For that integral, my electric field in all of this region is pointing straight up, and my L vector, or my dl vector, is pointing to the left. So the dot product of my electric field pointing up and my dl vector pointing to the left is just going to be 0 because they're perpendicular. So my second bit of line, E dot dl, or integral of E dot dl, is just 0 because of the perpendicular nature of the electric field and dl. For number 3, well, now I have my electric field is E1 z hat, and my dl vector here is going to be h in the negative z hat direction because my arrow is pointing downwards here. And then number 4, so this is 3, and then number 4, which is my bottom section, is 0 for the same reason as number 2, because the electric field and the dl vector are perpendicular to one another. Okay, so I can rewrite, so I'll box this off. So I can rewrite this as being equal to E2 times H minus E1 times H, where when I take the dot products, the z hats go away. And this is a nice, easy form for my integral here. We were able to save a lot of time by simply picking these lines in which the dot product, the integral of the dot product, was either 0 or just a constant. So this takes care of the left side of Faraday's law here. Now what we want to do is we want to take care of the right side. So I've set n equal to 0. N is just our number of loops, but we're only taking one loop. So I set n equal to 1, not 0. There we go. Set n equal to 1 because we only have one loop here. All right, so let's think about this magnetic flux. So the magnetic flux is simply the magnetic field dotted with the area vector for this loop, the area enclosed by the actual loop. Now, our area vector here, we do have to be careful. When we were doing Faraday's law before, we basically picked an area vector at random to say, oh, okay, the area vector has to be perpendicular to the surface, but that can be out of the board or into the board. But here we actually have to use a right-hand rule to figure out the area vector associated with this direction of looping around our DL here. So what happens is we curl our fingers in the direction of our arrows and our thumb points in the direction of the area vector associated with the area enclosed by this loop. So our dA vector looks like whatever the area is, and it's coming out of the board, which is in the negative y hat direction. So that is our dA vector, where we're going to actually have to work a little bit harder at this dA portion, but that at least gives us the direction. It points out of the board. Now let's consider the magnetic field. The magnetic field is going to be dotted with this dA. So any x or z components of the magnetic field are going to be completely killed off by the dot product. It's only going to pick out the y component. So let's allow our magnetic field here to be coming out of the board. So we have some magnetic field, and this is going to be in this region here. I'm just drawing it over here for space purposes. So let's assume that in this region we have a magnetic field coming out of the board. And we are going to also assume that this magnetic field is approximately uniform over this surface. Now the approximately uniform assumption allows us to simplify our life considerably, because if our magnetic field is uniform, well then first we'll say, well, my magnetic field points in the y direction, or in the negative y direction out of the board, in the same direction as my dA. So this just looks like the integral of b dA. I can get rid of the dot product since both of these things point in the same direction. And then I can pull the b outside of the integral, because I can pull anything that is constant outside of my integral. So then I just have b multiplied by the integral of dA. The integral of dA is just this area. And given the dimensions I've already listed, I can say that this then goes like b multiplied by delta x times h. That is the magnetic field multiplied by the width multiplied by the height. That is my area of my little loop there. So I have now found the magnetic flux as b multiplied by the magnitude of the magnetic field, specifically in the y direction here, because I've allowed my magnetic field to only have a y component, multiplied by this area. And now what we can do is we can try to take a derivative of that value here. So to simplify things in the beginning, let's consider, as opposed to taking a derivative, let's take the change in flux over to the change in time. So instead of ddt, we'll take delta of our flux divided by delta time. Okay, so then we can let negative ddt of b times delta x times h, and we'll allow that to go to negative delta of b times delta x times h divided by delta t. But our delta x and our h aren't changing over time. That's just the sides of our square here. So we can set this equal to negative delta x multiplied by h multiplied by the change in the magnetic field per time. All right, so now we have found relationships for the two sides of Faraday's law. We have a relationship for the left-hand side involving the difference of electric field between these two locations, and we have found an equation for the right-hand side involving the change in the magnetic field with respect to time. Okay. Giving myself a little room over here. Now what we can do is we can set these two sides equal to one another. So putting this in a slightly more readable form, I'm going to rewrite E2h minus E1h as this, and then I'm going to claim that this thing is actually just the change in the electric field. How much does the electric field change between E1 and E2, and I'm going to set that equal to negative delta x times h times delta b over delta t. And we can cancel out the h on both sides here because there's no reason to keep it around. And then we can move the delta x to the other side, and rewriting all of this, we get delta E over delta x equals negative delta B over delta T. And now that we have this final expression, we are going to turn it back into a derivative expression. So we're going to let our deltas become d's now. So we're going to say that this is the partial derivative of the electric field with respect to x, which is equal to the negative of the partial derivative of the magnetic field with respect to time. So by doing this analysis, we've been able to simplify Faraday's law from its original form into this relationship between a spatial derivative of the electric field. How is the electric field changing as we move in the x direction, with the change in the magnetic field over time. I should note that we're using partial derivatives here because in general the electric field will depend on time as well, and it could depend on x, y, and z. So there are many dependencies of the electric field, but we only want to know how it changes when we move in the x direction. Likewise, the magnetic field can also depend on all of the spatial dimensions along with time, but we want to know just how does the magnetic field change with time, and so we are taking the partial derivative of the magnetic field while holding the other variables constant. So that's why we're writing partial derivatives here. Now let's consider the exact same situation, except we're going to look at the magnetic field from the previous picture, and we're going to analyze that using the Maxwell Ampere relation. And we're not going to go through all of the steps quite so explicitly this time. We're just going to set things up and then kind of jump to the answer, because the steps are exactly the same with just the electric and magnetic fields flipped from our previous example. Okay, so now what we have is we are looking down on this same system that we had. We are looking at the magnetic fields, which are pointing in the negative y direction. So we've rotated our coordinate system. When we were looking at the electric field, we were looking kind of from the negative y direction. Now we're looking down on this from the positive z direction. Our magnetic fields still point in the negative y direction, just like they did on the last board. And our electric fields are going to be pointing out of the page here because our electric fields last time were pointing into the positive z direction, which is out of the page. Now, again, we need to create a closed loop and integrate the magnetic field around that closed loop, and then we need to find the integral of the electric field through that loop. So let's pick a loop. We are going to have our loop move in this direction around some border here. Again, we're going to get, as we do this integral of b dot dl, we're going to pick out the individual sides, and two of those sides are going to have 0 as b dot dl because they're perpendicular. So this side and this side, b dot dl will be 0, just like the horizontal lines had e dot dl equals 0 in the last board. And then we'll end up with our integral just containing these vertical portions there. Again, what we would do is we would take the electric field, find the area vector here, dot it with the electric field, take time derivatives in the exact same way that we did on the previous board. And what we're going to end up finding is that we have the partial derivative of the magnetic field with respect to x is equal to mu naught times epsilon naught times the partial derivative of the electric field with respect to t. Now, this looks just like the equation that we found on the previous board, except that we have these constants here, which are going to actually end up telling us about the speed of our wave. And we have reversed the positions of the electric and magnetic field. Now that we have our two differential equations here relating the electric and magnetic fields, what we're going to do is we're simply going to guess the answer as electric fields that go like some maximum amplitude multiplied by a cosine of kx minus omega t. And we'll remember that k represents the wave number, which is 2 pi divided by lambda, where lambda is the wavelength of the wave, and omega is the angular frequency, which is 2 pi multiplied by the normal frequency of the wave. A handy result that we are going to want to be able to use on these is that if we take omega divided by k, that looks like 2 pi f divided by 2 pi over lambda, which looks like lambda multiplied by f, which looks like the velocity of the wave. So we're going to want to remember this particular relationship here between omega and k, because it's going to come in handy when we want to figure out the velocity of these waves here. Okay, so let's actually plug these expressions for the electric and magnetic fields into our differential equations and see what we can find out. We're going to begin with this equation here. So the partial derivative of E with respect to x, well, taking a derivative of this, I'm going to get negative EM times k multiplied by the cosine of kx minus omega t. And if I take the partial derivative of the magnetic field with respect to t, I am going to get a Bm multiplied by omega. Sorry, this should be a sine. That's incorrect. Sine. This is a sine of kx minus omega t. Where in the case of our electric field, we picked up a minus sign here from the derivative of cosine is minus sine. And in the magnetic field case, we pick up a minus sign both from the derivative of the cosine and from the minus sign in front of the omega t term when we do the chain rule. And so we actually end up with a positive sign out front here. Okay, so we're going to set the negative of this equal to this, which means that we get Em times k times the sine of kx minus omega t equals the negative of, so this is negative, the negative of this sine of kx minus omega t. So now what we can do is we can cancel out the sine on both sides and say that the maximum value of the electric field divided by the maximum value of the magnetic field looks like omega divided by k, looks like the velocity, which we are going to knowingly call c, the speed of light. Okay, so our first equation here gives us that the ratio of the maximum strength of the electric field divided by the maximum strength of the magnetic field is equal to the velocity of our wave, which we are calling c. Now, let's solve this top equation, and we'll do it over here. So the derivative of the magnetic field with respect to x, well, that looks like negative k times the maximum value of the magnetic field multiplied by the sine of kx minus omega t. Again, the minus sign comes from the derivative of the cosine, and the partial derivative of the electric field with respect to time looks like negative, sorry, it should be a positive, omega Em sine of kx minus omega t. Now we can equate the negative of the derivative of the magnetic field x with our constant multiplied by this derivative here. So taking the negative of a negative gives us a positive, of course. So we have this for our negative partial b partial x. This is going to be equal to our constants multiplied by this partial derivative, which we can write mu naught epsilon naught omega Em sine of kx minus omega t. Again, we'll be able to cancel out the signs on both sides, and if we solve for Em over Bm, the maximum electric field divided by the maximum magnetic field, we end up with 1 divided by mu naught multiplied by epsilon naught multiplied by omega, and k is left on top from here. Remembering that omega divided by k is c, so therefore k divided by omega is going to be 1 over c. We can rewrite this as 1 over mu naught epsilon naught multiplied by c, the speed of light. And remembering that we called E over m c as well, we can write this as equal to c, or rather c equals the square root of 1 divided by mu naught multiplied by epsilon naught. And if you actually take these values, which can be found in the book, right, for the electric constant and the magnetic constant, you find that this is 3 times 10 to the 8th meters per second, which is exactly what the speed of light is. So what we find is that if we assume that our electric and magnetic fields look like cosine waves, we can plug that into our 2 Maxwell's equations that we are using here, and actually get that we get traveling waves which move at exactly the speed of light. So this is one of the biggest breakthroughs in the history of physics, to figure out that light is in fact electric and magnetic fields which are propagating each other. Remember that these came from the Faraday's law and the Maxwell Ampere's law, which talks about how changing magnetic fields creates electric fields, and changing electric field creates magnetic fields. And so to be able to turn this into a wave that propagates at exactly the speed of light is a huge accomplishment, and back when it was done in the 1800s was an enormous breakthrough for physics.